And the way to think of it, I think, is in terms of this particle having both wave-like and particle-like properties. It's spread out in space a little bit, and it's spread out in energy a little bit. Just a little bit, though, according to the uncertainty principle.
For many centuries, there had been a battle between the two pictures of light. And people like Newton, Isaac Newton, thought light was a particle. He said, well, it creates these sharp shadows. It doesn't really go around corners like a wave, so it must be a particle. And then other people, like Christian Huygens, who was a contemporary of Newton, he was a Dutch physicist, said that light is a wave because it has phenomena like diffraction and like and interference and refraction, the fact that you can see these bent images if you stick a rod into water. So there are these competing ideas. At the time of James Clerk Maxwell, the dominant idea was that light was a wave. And along came Einstein in 1905, and he said, no, light is grainy. It's a particle, which we later called a photon. What we now have, after about the middle of the 1920s, when quantum mechanics really became firmly entrenched, we have a sense that light can be either a wave or a particle. It's called wave-particle duality. And it can manifest its waviness in certain situations, and it can manifest its particle properties in other situations, depending on how we set up the experiment. It's a very counterintuitive notion.
Newton showed that you could take white light, separate it into its colors, and then, even better, this shows Newton's genius, you could take that rainbow and recombine it into white light with a prism running it through the other way. And that shows that inherent in light are all the different colors, whatever those colors are. But they didn't really understand what made the colors different from each other until much later, when once the wave nature of light became understood in the 19th century, then things really became controllable and understood much better. It was really the 19th century before we understood that light had a wave nature. And then, only at the end of the 19th century, did we understand that it has this truly particle nature as well. When you have something with a wave nature, they theorized in the 19th century, there must be something that's waving. If we go back to the pond with a piece of wood bobbing in the pond, you have the pond, and that's what is the medium for the wave. So what is the medium for light? And they thought it was the ether, some mysterious substance in which electromagnetism could propagate.
People thought that if you have a wave, if light is a wave, then it's got to have some medium to wave in. A wave is a disturbance in some kind of medium. Water waves, waves in water, the medium is water. Sound waves, the medium is air. So the physicists of the 19th century thought that light is a wave, and there must be some medium called the ether. The luminiferous ether, which was thought to be some very stiff, transparent medium through which the Earth moved as it went around its orbit, and light would, any light waves were oscillations in that ether. All right, and Einstein, with his theory of relativity, essentially shattered the ether. He said, we don't need an ether. If light is a particle, then it can come from the sun to my eye without any need for an intervening medium.